In Lesson 83, we're factoring special cases, and specifically, the special case we're going to spend some time with is called a difference of squares. Lesson 83 also deals with perfect square trinomials, but perfect square trinomials we're not going to really treat as a special case. We're going to factor those the same way that we've always factored trinomials. Okay, so it's not really new. The textbook will treat it as something new and make a big deal out of it. We're not going to make a big deal out of it being that much different from our regular trinomials. Okay, but before we do this, or as we do this, kind of a way of introduction, I want to go through just kind of a checklist of what we've done so far and what we still have left to do from a factoring perspective. So if we have two terms, if we're factoring two terms, the first thing that we always look at, and this goes all the way back to Unit 3 and Unit 4 of the class, and here we are in Unit 9, is a GCF. You gotta look for a GCF. That's got to be the very first thing that we look for. And if we have two terms, if we're factoring two terms, this is the only three things that you can factor, the only three factoring methods that are available to us. The first one is a GCF. The second method is the method we're going to use today, learn today, is difference of squares. Okay. The third method is probably going to be Algebra 2 for you guys. We won't look at cubes. I don't think we're going to get there. All right. We're getting close to the end of the year, so we're not going to make it to cubes in this class. I'll make it there in honors, but it's not that big a deal. It's easy. It's a form that you remember. But that's the only three things that you can have if you're told to factor two terms. Okay, so if we're factoring two terms, we're going to look for a GCF and a difference of squares, and then cubes, but that's going to be later for you. All right, so it's very, 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 very good to memorize this checklist. Two terms, GCF, difference of squares. For three terms, we're going to, first thing we're going to look for is a GCF. And then if we have a quadratic expression, we're going to use trial and error factoring. Now you're going to learn some different techniques for this in Algebra 2. In geometry, Ms. Fox is going to teach you another method for factoring quadratic trinomials. I just like to teach you the unfoiling process here. And some of the other tricks are good, but if you're not conditioned to checking it and going through the process, some of the tricks and little gimmicks that you use for factoring trinomials can actually get you the incorrect answer if you miss one little step in the process. So I prefer just trial and error factoring for the level where you guys are. So, in quadratic expressions, what we mean by quadratic expressions is, and this is lesson 84 actually. We're going to kind of further define this. Quadratic expression is anything that looks like this: ax squared plus bx plus c. 2x squared plus 10x minus 20. The kind of things that we've looked at just prior to this in our test review. Okay, so factoring quadratic expressions, if we have three terms, we're looking for a GCF, and then we are going to, for quadratic expressions, we're going to use trial and error factoring to unfoil it so that we have two things being multiplied by two things. Two linear binomials will multiply to give us a quadratic trinomial, three terms. All right, and also in Unit 9, we're going to introduce our final new factoring method, and that is for four or more terms. If we have four or more terms, it's usually going to be four. The first thing we look for is, guess what? GCF. And then after that, we're going to learn a new technique called factoring by grouping. And I will show you, and some students really like this a lot, I will show you when we do four terms, and that's in this unit, how to use grouping, the grouping method to factor these quadratic expressions. Some students that have struggled with trial and error factoring or other methods really like using grouping to factor the trinomials. I'll show you how that works. And this is really, factoring by grouping is really pretty easy. It works out pretty nicely. Okay, so today we're going to be right here, factoring difference of squares, and we'll be doing some quadratic trinomials as well, dealt with as a special case, and I'll show you what that is. But that's where we are in our factoring development here. So, determine whether each polynomial is a perfect square trinomial. If it is, factor it. Okay, and we're going to do this a little differently. We're going to determine whether it is a perfect square trinomial by factoring. We're just going to factor the expression and see if it's a perfect square trinomial or not.
Like we always do.
Yes. So you'll see these directions a lot in your homework. I don't want you to do what it's saying. I want you to see if it's a perfect square trinomial by factoring it. Okay? And what is the definition of a perfect square?
Something that multiplies by itself.
Something that is being multiplied times itself. Right? That's the definition of a perfect square. So what's the factorization of x squared plus 6x plus 9?
X plus 3 times x plus 3.
X plus 3 times x plus 3, and that is something multiplied times itself, isn't it?
Yes.
So x squared plus 6x plus 9 is a perfect square trinomial. All right? What about letter B? Can we find any factors of 4 that add up to be negative 2? Negative 2 and negative 2 add up to be negative 4. Negative 4 and negative 1 add up to be negative 5. So this is definitely not a perfect square. It's not factorable. It's prime. Okay?
Is this all we're doing?
Related to perfect squares, yes. So we're just wanting to identify by factoring whether something is a perfect square or not. All right, what about this last one? It's got some potential, doesn't it? How do you see that it has potential?
It has 8 in it.
Well, the first term and the last term are both what?
Perfect square.
Perfect squares. But what do we need to do first with this problem?
Divided by 8.
We need to take out a GCF of 4. Okay? So if I take out a GCF of 4, I'm going to have something that's a little bit easier to work with. 4 times 9x squared minus 12x plus 4. So 9 times negative 4 is, 9 times 4 is 36. Do I have any factors of 36 that add up to be negative 12? Negative 6 and negative 6 is correct. So this will be, and hopefully we're getting a little quicker at this, if I got to do negative 6x and negative 6x, which factors of 9x squared am I going to use? 3 and 3 is correct. Good. And then both of these will be minus 2. Is this a perfect square?
Yes.
Yes. Okay. So because this can factor as, and you could write this as 4 times 3x minus 2, 3x minus 2, or we could write it as what? 4 times 3x minus 2 squared. Alright, so if both binomials are the same, then it is a perfect square trinomial. There's a shortcut method for factoring this, but why learn another method? I never really saw the benefit of learning another method to factor these problems. We already know how to factor that. Why should we learn a different method just because it's a perfect square? I don't like the method either. It's a little bit, it's just, it's unnecessary. for where you are in your mathematical life. All right, let's have a look at example 2. It's a word problem. A cell phone tower signal covers a circular area. Circular area. What is that begging me to work with here? Pi times the radius squared. So that's the area of the tower. We don't know what the radius is. All right. Second sentence. The strength of the signal is increased. And it now covers an area of pi r squared plus 10 pi r plus 25 pi square miles. By how much did the radius of the coverage area increase? So by how much did the radius increase? Now, in the context of what we're doing, what are we going to use with this expression to see what's going on? We're going to factor it. We're going to factor pi r squared.
We can factor pi out.
We have to factor pi out, right? It's a GCF. I have no idea what to do with pi. I can't break it up into two things that multiply to be pi when I factor that. So pi goes into this r squared plus 10r plus 25 squared. And then all of a sudden I've got a really easy problem to factor, don't I?
Yes.
What are the factors of 25 that add up to be 10?
R plus 5.
R plus 5 times R plus 5, which I can write as, what Kyle says, R plus 5 squared. All right, so the original cell phone tower covered this area. This cell phone tower covers this area. How much did the radius increase?
By 5.
By 5. Okay, so the answer to our question is that it increased by 5 miles. The radius increased by 5 miles. This plus 5 tells us that the radius increase was 5 miles. All right? Good with that? Okay. Let's move on to next topic. Determine whether the binomial is a difference of two squares if first factor the binomial. And we're going to take a step out of the problem here because we need to cover something. We're going to examine this expression, difference of two squares.
Wait, what are we doing? I didn't see the problem.
You don't need the problem at the moment because it said to determine if it's a difference of two squares. Okay, let's take it apart. How would we recognize if something was a difference of two squares? What does difference mean? Subtract. I left something out of that, didn't I? Subtract. Subtracting to what? Squares. What are squares? What do we mean by squares? Numbers or variables that are what? Multiplied by themselves. So if we're talking about numbers, what are the numbers that are squares? 1's a square. 4's a square. 9's a square. Y'all work with me. 16, 25, 36, 49, 50, 64, 81, 100, 121, 144, 169, 196, 225, and we need to be familiar with those all the way up to 20. All right, and this is why we need to be familiar. We've been practicing being familiar with those. It's good for simplifying this. Now, how do you determine if a variable is a perfect square? And we've done this with simplifying radicals. If it's squared, it's obviously a square, but how else? What if the exponent is something else?
If it's like an odd number, you get the number.
If it's an odd number, it's not a square, right? But it has a square in it. So how do you determine if an exponent is a square? It has to have what kind of exponent? Even exponents. X to the 4th, x to the 6th, x to the 8th, x to the 20th, x squared. If the exponent is even, then it's a square. So what we're looking for when we're identifying two terms, y'all listen, everybody pay attention. If we're factoring two terms, we look for a GCF, and then we're looking for a difference of two squares next. What is the difference of two squares? It's two squares that are being subtracted. So they have to have different signs, because if they had the same signs, they would be what? Added. Right? You add things that have the same sign. Okay, so that is what we're going to be looking at here. So let me see if I can get out of this. Now, determine whether each binomial is a difference of two squares. If so, factor the binomial. Is this a difference of two squares?
No. Yes.
Yes.
It is, right? What's 4x squared the square of? 2 and x. And what's 25 the square of? 5. Now, difference of squares are really easy to factor. 4x is the square, 4x squared is the square of 2x. 25 is the square root of 5. But it has to be what? Negative 25, so that means one of these has to be positive and one of these has to be negative. Now, the relationship of these two terms, these are called conjugates. Okay? Conjugates. Difference of squares will always factor as conjugate pairs. A plus B, A minus B. X minus 5, X plus 5. 2x minus 5, 2x plus 5. Right? Conjugates are binomials that differ by one sign. Now, let me prove to you that this works. What's 2x times 2x? 4x squared. Negative 10x, positive 10x. There's no x, right? Do we have an x to the first term in our expression? We do not. It was 5 times negative 5. Negative 25. So it works, right? If we have a difference of squares, it will always factor as conjugate pairs. Difference of squares, really quick and easy if you know this. If you don't, then you just kind of have to guess at it, which we're not going to do. We're not guessers. We're mathematicians. Okay? Let me go back. Second one. 9m to the 4th minus 16n to the 6th.
Yes.
It's two terms. What do I have to look for first now? Remind me what I have to look for first.
The
GCF. Do we have a GCF here?
No.
No, 9 and 16 do not have anything in common. Now, do I have a difference of squares? We're certainly okay with the difference, right? They're different signs. They're being subtracted. Is 9m to the 4th a perfect square? Yes, right? Because 9 is a perfect square and the exponent is even. 16n to the 6th, is that a perfect square?
Yes.
It is, because the 16 is a perfect square and the exponent is even. Right? So what is 9m to the 4th the square of?
3m
squared. And
4n to the 3rd.
4n to the 3rd. And these have to be conjugates. Positive, negative.
But how would you get, if you do both 4 into the 3rd when you multiply?
When you multiply, you add exponents.
Oh, yeah.
So n to the 3rd times n to the 3rd is n to the 6th. Pretty easy, right?
Like once you figure out like what the perfect square of that is and then what the perfect square of that is, it's the same thing, except we just gotta make sure
One's positive, one's negative. They have to be conjugates.
Okay.
The formula for factoring the difference of squares, and this is in your textbook, if you have difference of squares, a squared minus b squared will always factor as a minus b times a plus b. Or a plus b times a minus b. The conjugates, that's the formula. Okay? A squared minus B squared is A plus B times A minus B. Because negative AB and positive AB will cancel each other out. So we don't get that middle term to bust up. There is no middle term there to bust up, like there is in the trinomials. Now this is still a quadratic expression because it has a square in it, but it's not a quadratic trinomial, it's a quadratic binomial. To factor a quadratic binomial, we look for GCF, and we look for a difference of squares. If it's not that, we're stopping for now. If we get to cubes, I'll show you how to factor cubes. All right? Now, let's look at one more. X squared minus 8. Do we have a GCF?
No.
Do we have a difference of squares? Why not? 8's not a perfect square. Okay? It's not factorable over the rational numbers. This is it. You can't do anything to it. Now, we could go into the irrational numbers because 8 has a square root, doesn't it? It's the square root of 8. So you could factor this as, I don't want to go forward, I want to go backward.
It's not asking.
And I'm not going to require you to do this, but you could factor this as x plus the square root of 8 times x minus the square root of 8.
You probably don't have to do
You don't have to do that. But that is, 8 does have a square root, it's just not a perfect square. And we're interested in these two squares being perfect squares. All right? The square of an integer. All right, last one. Negative 64 plus z to the 8th.
Yeah.
No square, no GCF.
No GCF. Is it a difference of squares?
Yeah.
Yes.
Yes.
Because how could I write this? Couldn't I write this as
Negative 8.
z to the 8th minus 64? And now it's pretty obvious that it's a difference of two squares, right? As long as the signs are different, you're going to subtract. Okay, so what is z to the 8th the square of?
0.
Z to the 4th. Okay, and 64 is the square of
Negative
8
8
plus minus.
You could have picked which one you would have do the plus or minus 8 for, right? Does it have to be in a particular order?
No, it doesn't have to be. You could do z to the 4th minus 8 and then plus 8. They just have to be conjugates. One has to be positive, one has to be negative. Okay? Differ by one sign. All right. Good job, guys. Let's see what else we got here. Ganesh.
that. Is that.
They have to be very multicultural here. Ganesh is designing a square border around a square pond. The area of the pond is 225 square feet. Use the difference of two squares to write an expression that represents the area of the border. Now, this, guys, is really, really a common scenario that you'll see in geometry. It really is. This is preparing you for what you kind of would see in geometry related to this. The area of the border. Now, the border is the white part that they have. You know, they're showing us here. The border is this part that's outside the pond but inside the fence. So we want the area of that. So how would we find that area?
The root of 225.
No, the area of the pond itself is 225. So this part is 225. It's going to be opposite of that.
You plus it.
It's the whole area. What's the area of the whole thing? This whole square has an area of what? 4f squared. The area of the pond, I would subtract it. It's like we're taking the pond out of the equation. Is 225. Use the difference of two squares to write an expression that represents the area of the border. Is that a difference of two squares?
No.
Yeah, it's 2f squared, and negative 225 is the square of 15.
So you can just leave it like that. You don't have to-
Yeah. It doesn't say factor it, it just says write it as a difference of two squares. That is a difference of two squares. Now, if you did factor it, you'd be okay. The factorization of this would be 2f minus 15 times 2f plus 15. So you could write it like that. Okay? Here's your homework. 546, A through C, E through H, 1 through 9, 12, 13, 17, 24 through 26, 28, and 29. Now, remember, I want you to remember, it's very important, if it says to determine if it's a perfect square trinomial and then factor it, that's not what we're going to do, right? We're going to determine whether it's a perfect square trinomial by factoring it. So factor it, and if it's something times itself, it is. If it's not, then it's not a perfect square trinomial.